If you are speaking, I am not hearing you. Where would you like us to start today? All right. Sure. Absolutely. And you're welcome to mute yourself as needed.
Okay, can you hear me?
Yes. I can hear you just fine.
Okay,
Where would you
sorry.
like us to start?
Can we
And
start with one?
hopefully you heard all of that, what I said before.
Yes, I did.
Okay, excellent. Where would you like us to start?
Number one.
Number one. Okay. That's the challenge here. I got all these pictures in front of me. I can't tell you which one is number one. Let me,
Oh, it's that
I
one.
see. Okay, there we go. It's the police cruiser.
Yes.
All right, very good. Let me snip that into my workspace here, and we'll get started looking at that one. All right. Police cruiser approaching a right angle intersection from the north is chasing a speeding car that's turned and is now moving straight east. When the cruiser is 0.6 miles north of the intersection, the car is 0.8 miles to the east. The police determine the distance between them, and the car is increasing 20 miles per hour, cruising 60 miles per hour. Okay, blah, blah. Right. It's a really complicated way of saying, okay, the cruiser's going this way and the car is going that way. And the cruiser is 0.6 miles or 0.8 miles. The car is moving at a speed of 20 and the cruiser is moving at a speed of 60. Sorry, that's not quite right. The car is increasing at 20 miles per hour. No, the distance between them, sorry, this is confusing to read. The distance between them is increasing at 20 miles per hour. So I'm going to call that D prime. And this thick D is the Y prime of the cruiser. Hopefully you've seen that before in
Is
class.
that like DXDT?
Yeah, so let me use different notation. What do you want to call the hypotenuse? Do you want to call it, normally it's X, Y, and then I don't know what to suggest with students because they're usually a little uncomfortable. What do you want to
I
call
just
it
use
there?
Z.
Z. Z is a good one. Okay. So yes, dy dt is 60. dz dt is 20. And they want us to find dx dt in this problem. Is that clear?
Yeah.
All right. So the way you do this is you need some overarching equation. Well, that's the Pythagorean theorem. X squared plus y squared equals z squared. You're going to use this in two ways. The first way you're going to use it is to find z. So 0.6 squared plus 0.8 squared equals z squared. You'll find that z equals 1 when you solve that. And if you need some more explanation on that, I'm happy to provide that. The next thing is you have to take a derivative of this. Is that something you've
Okay.
been doing in class? Got familiarity
Yes.
with? So
Yeah.
it's 2x dx dt. It's a related rate. 2y dy dt equals 2z dz dt. They all have a 2, so you should cancel them all out. Gone, gone, gone. And then you figure out which one you're solving for. Because in another problem, it might be that you're solving for, a different one. So dx dt in this problem, you're going to move the y dy dt to the right. So you have z dz dt minus y dy dt, and then you're going to divide by x or multiply by the reciprocal, something like that. And from here, it's just a matter of putting those numbers back into the problem. Any questions on what I've done up to this point?
No.
Okay, so now it's just putting the numbers in. So we found that z is 1, z dt is 20, y is 0.6, dy dt is 60, and then x was 0.8. Are you allowed to use a calculator?
Yes.
Okay, so you can put that in a calculator and get your final answer.
Let me see.
And the units are important, so that would be miles per hour.
Okay, I got -20.
Okay. There's a small unclear. It's one thing that's kind of unclear is whether um they don't specify the direction of z. Z could be negative. The ZDT could be negative. It's a little unclear from the problem,
Okay.
which impacts the answer. So I don't know. So that's sometimes I get these problems and I don't have the full scope of what you guys are doing.
So that's the speed of the car?
Yeah.
Okay.
I don't really like the question, but that's what they've given. So we're gonna, we gotta go with that. Which one do you want us to look at next?
Can we do the rectangular tank one? It's number 5.
Yes, if I can find it. All right, there it is. Yes, the lovely rectangular tank. All right. Um, a open top rectangular tank with square base X on a side and Y feet deep is to be built with the top flush with the ground to catch runoff water. Excavation charge proportional to product XY. Okay. If the cost is what values of X will minimize the cost. All right. So you've got to draw a picture. So the rectangular tank here, something like this, X and Y. So the volume is X squared Y. The volume is given as 1125 equals X squared Y. Is that okay?
Yeah.
Now, this is kind of a variation on the traditional problem here. Typically that you maximize like surface area or something, but they're telling you like, oh, this is the cost equation that you care about. Notice it's a function of both X and Y, which is bad because you don't know how to take derivatives of two variables yet. You will if you take calculus 3. So you have to use this equation and probably solve for Y. Y is 1125 over X squared. And you're going to put that back into the given equation here. And it is a good idea to simplify. So that becomes whatever it becomes, 5x squared plus 20 times 1125 over x squared plus 10 times 1125 over x, something like that. Now, are these pure calculator problems?
Um,
Like, because the next thing here that we're gonna take a derivative and set it equals 0, but this one probably not be able to solve by hand. Um,
so I multiply 20 times 1125.
uh, yeah, that's not, yeah, I mean, that's not super important. We got to take a derivative next, though. So
Okay.
your derivative is 10x minus 2 times 20 times 1125 over x cubed minus 10 times 1125 over x squared. And you have to set this equal to 0. And this part is hard to solve. That's why I'm asking if this was designed as a calculator problem.
I think so, but I really don't know.
Okay. Well, that's where I need to know that information to best help you. I'm going to go ahead and just graph it because that would be the most reasonable way to proceed here without knowing anything else, assuming you've got some sort of a calculator available to you.
Oh yeah, I do.
Okay. X cubed 10 times 11, 25 for x squared. I mean, this kind of has the feel of an AP style question. Let me get a better picture of this. All right. So here's a snip of the graph. And you can see that the only x value that makes any sense is this one right here. X is 11.489. So they want the values of x and y that'll minimize the cost. You can get y from this other equation. And so you would divide this by x squared there. Something like that. So I get 8.52 for that. We should put in proper units, whatever they are in the problem. Feet, feet, feet. Any questions on that?
Oh,
Okay.
okay, yeah, good.
All right. Give a possible scenario for the cost function in A. What they're hoping you're going to recognize is that, grab the snip of this. Is that the x squared, um, sorry, so this is for the base. So the scenario here is that the base is $5 per unit. These are the sides. There's 4 of them, so it's also $5 per unit. XY is another side. Um, so, but they already say it's proportional to the product. I don't know. So you could call this maybe the, yeah, I don't know. So I think my guess is they just want you to focus on this first part. Yeah, these the cost of the materials. Because they tell you that that this is the excavation charge in the problem.
Okay,
I believe that is everything for that one.
all right. Do we still have time for one more?
Yes, yeah, no, we're gonna go till another 10 minutes or so.
Okay, can we do um the conveyor belt one? It's number 3.
Sure. All right, so I will send you an email at the end as well with the notes and a link to the screen recording, which will be up tomorrow or next day maybe. But yeah, I mean, go through as much as we can here. So sand falls from a conveyor belt at a rate of 10 meters cubed per minute. So the units tell you that that's a V prime. The meters cubed tells you that that's a V prime. The height of the pile is always 3/8 the base of the diameter. How fast are the height and radius changing when the pile is 4 meters high? Give your answer in centimeters. Okay. So it's a conical pile, I guess. I don't know how you're supposed to know that. But it says it. Okay. So, I always ask students here, like, is your instructor going to give you the formula for the volume of, a cone in this case? It's 1/3 pi r squared h. Do you think you'll be given that formula?
Yes.
Oh, that's good. So the diameter is 2 times the radius. The height is always 3/8 base diameter. Okay. So there's a little bit of deception in this problem here. You've got to know that the diameter is double the radius. The height, it's 3/8 2r. Height is 3/4 r, like that. Um, so typically you put that in here, and this you put that in for h. You get it down to one variable. So volume is 1/3 pi r squared 3/4 r, like that. So when you simplify here, the 1/3 and the 3/4 make fourth pi r cubed. And then now you're ready to take a derivative. dv dt equals 3/4 pi r squared dr dt. So we can solve for dr dt in this problem because we're given dv dt. dv dt is 10, 3/4 pi. The radius is not given. It just says that the height is 4. So we have to go back to this formula here. The radius is 4/3 times the height. That's from this equation. So the radius is 4/3 times 4, or 16/3. So we're going to put that into this part, 16/3 squared dr dt. So we have 3/4 pi 256/9 dr dt equals 10. So now it's just a matter of kind of moving some things around. So it's 4/3 times 10. You're going to put a pi on the bottom. And then you got a 9, 256 equals dr dt. So you get some cancellations. 3 goes into 9 3 times. 4 goes into 256, 128/64. And then 5 and 32. So you end up getting, doesn't look great, but it's 15/32 pi equals dr dt. To find the dt, we go back to this equation here. We can use this one, or I don't know. We can use any of these on the left here. We'll use this one. It's probably the more standard one. So dr dt, which we just found, equals 4/3 dh dt, which is what we want to find. So dh dt is 3/4 dr dt. So it's 3/4 of the 15/32 pi, which ends up being 45/128 pi. And then we need units. We should have included units in these. This is meters squared per minute, and this is also meters squared per minute. Hopefully that wasn't too quick to be able to follow.
That's good.
Let me know if you need any time to get this down.
What does it say right there?
On
Is
the
it
right here,
meters squared? Yeah.
meters squared per minute, yeah. Handwriting gets worse and worse every late night.
And then we just gotta put it in centimeters?
Oh, is it asking for the answer in centimeters? I didn't even
Yes.
pay attention to that. So that suggests it's a calculator thing now, but Yeah, I mean, if the answer is in, did I miss something here? Sorry, I'm just bothered by that. Why? And it's an unnecessary unit conversion too. Um, so why do they want transfer in centimeters per minute? Okay, well, that's stupid. So, sorry, meter squared per minute. So, in 1 meter, there are 100 centimeters. So yeah, to get the squared, you square the top and the bottom, and that's how you proceed. You basically just multiply your answer by 100 squared.
Okay.
Okay. What else?
Um, number 10.
10. Find the rate of change of the distance between the origin and a moving point on the graph of y equals x squared plus 1. 2, 5, the y-coordinate increases a rate of 4 centimeters per second. Okay, so you have to know the distance formula, which is y2 minus y1 squared plus x2 minus x1 squared. You can do the distance squared. You don't have to use the square root. Sometimes that saves you some time here. We know that it's the distance between this function, which is x comma x squared plus 1. So the y2 is really x squared plus 1 minus 0 squared. Plus x minus 0 squared like that. That's the distance squared. Now, why are they giving the fact the y-coordinate increases? I don't know. Okay. Anyway, so we have x squared plus 1 squared plus x squared. And we got to take a derivative. So you've been using z, so maybe I should switch that to z. Maybe your instructor wants that. It's weird. Okay. Um, so I think your teacher wants you to say x squared plus y squared here instead of z squared. X squared plus y squared is z squared.
Mhm.
I'm not really sure because this is an odd problem. One of the things that does happen here is that the x squareds do cancel. And now when we take our derivative here, we get 2y dy dt equals 2x squared plus 1 times 2x. And then you can divide everything by 2y here on the left and the right. So dy dt is 4. They're telling you that it's 4. And does that equal that? Rate of change between origin and point of the y-coordinate increases at a rate of 4 centimeters per second. Maybe they want you to do it differently. Z squared equals x minus 0 squared plus y minus 0 squared. Okay, so 2z z dt. This ends up being 2x dx dt plus 2y dy dt. So we're solving for this. What we don't know is this, though. and what can we presume it to be? So I think what you've got to find here, and because we can find everything else. Kind of like that earlier problem we did. The z dt equals x dx dt plus y dy dt times 1 over z. And z is equal to the square root of x squared plus y squared. So this becomes, z ends up being the square root of 2 squared plus 5 squared, which is the square root of 29. I guess we can try and get x from this over here. So I think that's probably how they want you to do it. dy dt equals 2x dx dt. So since dy dt is 4 and x is 2, we get dx dt equals 1 when you solve this. Looks to be the only way. So that's 2 times 1 plus 5 times 4 times 1 over the square root of 29. So it looks like it's 2 plus 20, 22 over the square root of 29 as your final answer. Okay, we do have to stop there for today.